the science of tsunamis, and how to predict them. They come without warning, rising from the deep like silent giants. And when they strike, they leave behind nothing but devastation. Tsunamis, some of the most terrifying and powerful forces on Earth. But what really causes a tsunami? Can we predict them before they hit? And how can science help us prepare for the next one? This is the story of how we're learning to understand nature's most devastating wave. It starts deep beneath the ocean floor. Imagine two massive slabs of Earth's crust, tectonic plates, locked in a slow-motion battle, pressing against each other for decades, even centuries. Then suddenly they snap. In an instant, one plate lurches upward, releasing a burst of energy so powerful it displaces an enormous column of seawater above it. That's how most tsunamis begin, with an undersea earthquake. It's not the shaking itself that's deadly. It's what the ocean does next. The energy from that quake ripples outward in all directions, creating waves that travel across the sea at jetliner speeds, up to 500 miles per hour. In deep water, those waves might be just a few feet tall. You wouldn't even notice them passing under a ship. But as they approach the shore, everything changes. The ocean floor gets shallower, the wave slows down, but the energy, the power, has nowhere to go but up. The wave begins to grow, and grow, and grow. By the time it reaches the coast, it's no longer just a wave, it's a wall of water, sometimes 30, 50, even 100 feet tall. It crashes onto land with unstoppable force, destroying buildings, uprooting trees, sweeping away cars, boats, bridges, everything in its path. And it doesn't stop with one wave. Tsunamis often come in a series. The second or third wave is sometimes the biggest, and the flooding can continue for hours. This is the destructive reality of a tsunami. But it's also a puzzle, because for years, humanity had almost no way to see them coming. So how do we detect something that moves invisibly across the ocean? That's where science comes in. Today, we use a network of seismographs to detect undersea earthquakes almost instantly. These instruments record vibrations in the Earth's crust, alerting scientists within seconds when a quake hits. But not all undersea earthquakes cause tsunamis, so we need more data. That's why scientists also use special ocean buoys, called DART systems, short for Deep Ocean Assessment and Reporting of Tsunamis. Each buoy floats on the surface and connects to a sensor anchored to the seafloor. If a tsunami wave passes overhead, the pressure at the bottom changes. The sensor detects it. The buoy transmits a signal to satellites, and that signal is sent to tsunami warning centers around the world. This system buys us precious time. Depending on where the earthquake occurs, coastal communities might have minutes or even several hours to evacuate. It's not perfect, but it's saving lives. But earthquakes aren't the only cause of tsunamis. Underwater landslides can trigger them too, like when a chunk of continental shelf collapses and displaces water. Volcanic eruptions can also launch massive waves, especially if part of the volcano collapses into the sea. One of the most recent examples? In 2022, an underwater volcano erupted near Tonga in the South Pacific. The explosion was so powerful, it sent tsunami waves rippling across the entire Pacific Ocean. Even asteroids crashing into the ocean could, in theory, trigger massive tsunamis. That's why scientists are constantly studying historical records, geological clues, and computer models to better understand what causes tsunamis, how they behave, and where they're likely to strike next. History has taught us just how deadly these waves can be. In 2004, an undersea earthquake off the coast of Sumatra unleashed one of the deadliest tsunamis in recorded history. It killed over 230,000 people across 14 countries. Entire towns were erased from the map in minutes. There was almost no warning, and many communities had no idea what was coming. In 2011, Japan experienced a powerful 9.0 earthquake off its eastern coast. The resulting tsunami was over 130 feet tall in some places. It swept inland, overtopped seawalls, killed nearly 20,000 people, and triggered a nuclear meltdown at the Fukushima Daiichi power plant. These disasters changed everything. They pushed scientists, engineers, and governments to act faster, build better detection systems, and educate the public about what to do when the water pulls back from the shore. Because that's one of the few natural warning signs we can see with our own eyes. If the ocean suddenly recedes, exposing the seafloor, it could mean a tsunami is seconds away. That's your cue to run, immediately. So where do we stand today? We've made huge progress. Tsunami warning centers now cover major oceans. Seafloor sensors are more accurate and faster than ever. We can simulate tsunami scenarios using advanced computer models, and some cities have built vertical evacuation towers for people to climb when roads are blocked. But challenges remain. Many coastal areas still don't have early warning systems. Education and drills are lacking in high-risk regions. And no technology in the world can stop a tsunami once it starts. Our best defense is preparation. That means investing in science, improving infrastructure, and most of all, spreading awareness. Because the more people understand how tsunamis work, the better chance we have of surviving the next one. Tsunamis are awe-inspiring reminders of nature's raw power. They can't be tamed, they can't be bargained with. But they can be studied, they can be tracked, and with the right science and the right action, they can be survived, because every second counts. And when the wave comes, knowledge is the strongest lifeline we have.